Good afternoon. Today I will explain the integral test, a convergent test that connects an infinite series with the area under a curve. I will begin by stating exactly what the test establishes. Then I will briefly explain its historical origin and prove it using the rectangle comparison from our textbook. Finally, I will present three recurrent cases, one convergent series, one divergent series, and one series for which the integral test cannot be applied. The integral test begins with a sequence whose terms can be represented by a function. In other words, we need to write a sub n as f of n. The function must satisfy three main conditions. It must be positive, continuous, and decreasing for x greater than or equal to 1. If these conditions are satisfied, the infinite series from n equals 1 to infinity of a sub n and the improper interval from 1 to infinity of f of x have the same convergence behavior. This means that if the integral converges, the series also converges. If the integral diverges, the series also diverges. However, the series and the integral do not generally have the same numerical value. The integral is only used to determine convergence or divergence. If we talk about its historical origin, it would be inaccurate to create the integral test to only one mathematician. In 1742, the Scottish mathematician Colin Maclaurin published the basic integral comparison in his book, A Treatise of Fluxions. Maclaurin's idea was geometric. He compared the terms of a series with rectangles placed under or above a positive decreasing curve. This allowed him to compare infinite sums with an area. Later, in 1821, the French mathematician Augustin Louis Cauchy published Cours d'analyse. Cauchy developed a more systematic theory of limits, partial sums, convergence, and divergence. Maclaurin provided the geometric comparison, while Cauchy supplied much of the rigorous language used in modern proof. For this reason, the result is sometimes called the Maclaurin and Cauchy integral test. The slide shows the central idea of the proof from our textbook. Because of f Because f is decreasing, the height of the curve becomes smaller as x increases. In the first figure, the rectangle has points. Each rectangle lies below the curve. Therefore, the combined area of these rectangles is less than or equal to the area under the curve. This gives the first inequality, a 2 plus a 3, continuing through a sub n, is less than or equal to the interval from 1 to n of f of x. In the second figure, the rectangles use left endpoints. These rectangles lie above the curve. Therefore, the area under the curve is less than or equal to a1 plus a2 continuing through a sub n minus 1. Together, these inequalities trap the interval between two expressions involving the partial sums of the series. We can now use these inequalities to prove both directions of the integral test. First, suppose that the improper integral converges. The sum from I equals 2n of a sub I is less than or equal to the improper integral. Therefore, the partial sum s sub n is bounded above by the first term plus the value of the integral. We call this upper bound m, capital L. The partial sums are also increasing because every term a sub n is positive. An increasing sequence that is bounded above must converge, therefore the series converges. Now suppose that the improper integral diverges. The second inequality shows that the integral is less than or equal to the partial sum s sub n minus 1. If the integral grows without bound, the partial sums, which are even larger, must also grow without bound. Therefore, the series diverges. This proves that the series and the improper integral have the same convergence behavior. For the convergent case, consider the series from n equals 1 to infinity of 1 over n equal plus squared plus 1. The corresponding function is f of x equals 1 over x squared plus 1. This function is positive and continues for x greater than or equal to 1. It is also decreasing because its derivative is negative in this interval. The improper integral from 1 to infinity of 1 over x squared plus 1 is evaluated using the inverse tangent. The result is pi over 2 minus pi over 4, which equals pi over 4. Because this value is finite, the improper integral converges. Therefore, by the integral test, the series converges. Notice that pi over 4 is the value of the integral. It is not the exact sum of the series. For the divergent case, consider the series from n equals 1 to infinity of 1 over n plus 1. The corresponding function is f of x equals 1 over x plus 1. This function is positive, continuous, and decreasing, so the integral test can be applied. When we evaluate the improper integral, we obtain a logarithm expression. As the upper limit approaches infinity, the logarithm also approaches infinity. Therefore, the improper integral diverges. By the integral test, the series also diverges. This result is reasonable because this series is shifted version of harmonic series, which is known to diverge. The third case is the alternating harmonic series. The sum from n equals 1 to infinity of negative 1 raised to n plus 1 divided by n. The integral test cannot be applied because the terms alternate between positive and negative values. Therefore, the positive condition is not satisfied. At this point, the integral test gives no conclusion, so we must use the different test. We use the alternating series test and define b sub n as 1 over n. The sequence b sub n is decreasing and its limit as n approaches infinity is 0. Therefore, the series converges by the alternating series test. However, the absolute value series is the harmonic series, which diverges. Therefore, the original alternating series converges conditionally. To decide whether the integral test is appropriate, we should ask four questions. Can terms be represented by a function? Is the function positive and continuous? Is it decreasing? And can we evaluate the corresponding improper integral? The three main ideas are these. The series and the integral have the same convergence behavior but not necessarily the same value. The decreasing condition creates the upper and lower rectangle comparison used in the proof. Finally, if one of the conditions fails, we must select another convergence test. The integral test usually answers the questions: does the series converge? It usually does not answer the question, what is the exact sum? This was all, and thank you very much.